Good afternoon, everyone. Thank you very much for joining this session. My name is E.H.Lee. I'm an associate professor at Sungkyunkwan University in South Korea. Unfortunately, I couldn't be there in person today since I am also organizing another conference here in Korea. But I'm really happy to have this opportunity to share my research and listen to other inspiring talks online. Today, I'll be talking about implementation of AI models and data for real-time control and decision-making in manufacturing equipment. In simple terms, our study focuses on connecting data, AI, and machines to realize autonomous manufacturing system, which is one of the important physical AI technologies. I'd like to mention that Jiun Kim, one of my PhD students, has contributed a lot to this work, and also this work was supported by Hyundai Mobis. Recently, manufacturing has been evolving beyond the concept of smart factory toward what we call an autonomous manufacturing system, AMS. AMS not only automates manufacturing but also help to address the issues of rising labor costs and safety concerns. This technology is becoming increasingly essential as the global population decline becomes a serious reality. In addition, AMS allows multiple products to be produced on a single production line, eliminating the need to build new lines for each product type and significantly reducing setup cost. These advances require manufacturing equipment capable of decision making directly, real time, and powered by data and AI. Our lab is conducting research in collaboration with several companies to apply AMS technologies across various fields, including automotive, home appliance, and aerospace industries. Since the time is limited today, I will focus on one specific example, our work with Hyundai Mobis, where we implemented AMS in automotive motor manufacturing process. Before going into details, I would like to briefly discuss the difference between a smart factory and autonomous manufacturing. Of course, depending on how we define each system, this discussion can vary slightly, but I will take a general perspective here. Both systems are similar in that they make decisions based on data and automate manufacturing processes. However, the key difference lies in who makes the decision. In smart factory, decisions are made by humans based on data. Whereas in autonomous manufacturing, decisions are made automatically by machines or system itself. The important point here is that humans find it difficult to form a complete closed loop between data and machines control. However, if the system itself can make decisions directly, it becomes possible to realize a self-governing production system with closed-loop decision and execution. This theoretically enables a faster and more efficient system, although implementing it in practice is highly challenging. As shown in this conceptual drawing, in AMS, AI must comprehensively manage real-time data obtained from the equipment and control component and their interconnect between machines, all within closed loop. At the same time, the system must perform real-time reasoning and control based on continuously changing data while ensuring both accuracy and speed. Since the time scale for decision making in manufacturing equipment is often within milliseconds, the system must be even faster than humanoid robot. Therefore, it is essential to carefully balance decision accuracy and processing speed. However, in general, there exists a trade-off between the accuracy and speed of AI models. Thus, deep analysis and customization of these models are required for each process implementation. In our lab, we have been studying the application of autonomous manufacturing technologies in industries such as automotive, home appliance, and battery manufacturing. Today's talk is focused on EV traction motors. Among the many components of an EV, the traction motor requires a high degree of customization to meet performance and demand. Various design optimization strategies are already available through simulation tools, but however, in manufacturing, it is often difficult to realize these designs because of process constraints. A flexible manufacturing approach is therefore necessary to bridge this gap between optimal design and practical production. EV traction motor commonly used U-shaped hairpin coils, which are made by forming flat wire copper wires. The coil manufacturing consists of this kind of processes: wire straightening, striping, cutting, bending, and assembly. I think many of you are not familiar with EV motor manufacturing. I prepared a short animation. This is the straightening, striping, cutting, moving into the bending machine. This is the bending process. Inserting here, and then finally welding. There are several challenges in wire forming. First, the loading passes are non-linear, which makes it difficult to predict spring back. You can think of this as similar to bending a paper clip. When you bend it, it doesn't stay exactly in the bent shape, but slightly returns to the spring back. The same phenomena occurs in hairpin coil. After forming, they tend to spring back, making it difficult to maintain the intended shape required for insertion into the stator. Second, the results depend on both material properties and wire dimensions. Third, these material properties even changes during the forming due to the plastic deformation. All these factors increase the complexity of controlling the process line in real time. Today we are focusing on this stretching line. Of course, our lab is doing all the processes, but due to the time limit, we will focusing on the straightening process in this topic. And also, to overcome these issues, we need to a flexible manufacturing approach like that. So the autonomous manufacturing system for the EV motor consists of three key components. The first, the sensors like here measured real-time changes in both dimensions and material properties of the wire. Second, this edge pitch. Edge pitch processes this input data and computes the optimal process control parameters using an MLP-based surrogate model, and also with some optimization or with some algorithm. Finally, the servo straighteners are here. They apply real-time control actions based on these computed parameters. The sensor systems measure two important input variables, dimensions and material properties. This set will measure the thickness of the wire. This set will measure the width of the wire. And also we made this eddy current proof. This will measure material properties in real time. This slide shows a real-time data measured by our sensors on an actual EV hairpin coil manufacturing line. As you can see here, the coil moves in periodic motion and stopping briefly at regular interval. At this stop, we measure material dimensions and material properties with the sensors. However, the raw sensor data cannot be used directly because, as shown here, the sensor regarding are affected by temperature variations. So we need to apply temperature compensation. You can see some temperature variation will affect the data, but even the vibration effect is much greater, like here in idly. If the sensor only measure the material properties, the data should be distributed like this red dot, like this way. But in reality, the machine vibration will affect the sensor data, and then the real data are spread out like this blue dot. We need to make some compensation for the temperature effect and vibration effect, and we had spent 3 years to make this compensation. And finally, we can get this very good data in real time in real manufacturing line. This black one is, this data is before the straightening, but during the straightening, because of the plastic deformation, yield stress was increased like this one, and after we measure after straightening, we can get this red data. Because of the plastic hardening, the yield stress was increased. And also you can see this one is one lot data here, and we change the bobbin, and the initial data will be slightly different. The property is different during this general data, so that we need to consider this kind of variation of material properties. How about that? Many people, they think that if we gather a lot of data, this data will increase the model accuracy. In theory, it is right, but reality is more complex, because if you gather more data, which means that you gathered more noise. So that you gathered a lot of data, then you gather more noise, so you need to figure out which is noise and which is real data. This requires a lot of time to figure it out, so that in reality it is not easy, so that you need to think another strategy to use this kind of method into real manufacturing. I'll be talking about it later slides. And this is a straightening. Okay, this is a servo system control the displacement of each roller using servo motors. This one is a very traditional thing. As I told you, if this one cannot make a closed loop control system, so if you face, traditionally you face some quality issue in your product, you stop your line, then some people going into this machine, that they are making some manual screw adjustment like this way. Then after this adjustment, you return your line, then you will check your quality. This is not closed loop, this is open loop. But if you use this kind of system, this system measure material property and making direct decision and making real-time feedback, and then after that this servo straightener will make some real-time control, so we can make real closed loop autonomous manufacturing system. And also we need to talk about how we made the model. So we use two kind of strategies. The first group is physical experiment, and second data group is gathered by FEM simulation. And these two categories, each category had some advantages and disadvantages like this way. Physical experiment can consider very specific environment like roll, friction or other things, but it will make a lot of noise, and also it will have some outlier. But FEM simulation cannot consider very specific environment, but it does not have noise, it does not have outlier. It will follow the data is very stable because they are following some governing equations based on physics law, so that this FEM simulation data is much inexpensive, so that we can gather more data, so that we combine these two categories. This is the outline of our work, how we made the model. The first thing, in offline, we gathered a lot of data from the simulation, and then this simulation will give us some stable and amount of data, a large amount of data. Then we gathered here, then we first made pre-trained MLP modeling based on surrogate model, and this one is supervised learning. But after we made this first pre-trained model, and then we implement this model into the real machines, and then now we gathered real-time sensing data. But as I told you, this simulation does not include very specific manufacturing environment, so that with this sensing data will include a lot of very specific manufacturing environment. So we need to do some transfer learning, like a fine-tuning method. That after that we made the second fine-tuned model. Then we implement the final model into the machine. But each machines, even though you implement your model into the one type machine, but machines are totally different because machines have some different gear, some tolerance like this way, and also you can measure, you can see some shifting of the fencing, so you will see some degradation of the machine, so that you need to do some reinforcement running again for your each machine. And this is a synthetic data generation. We gathered our data from the FEM simulation. So we did Latin hypercube sampling, and then we gathered 400 random samples with different thickness, width, initial plastic strain. So our first pre-trained MLP-based model trained to predict curvature and plastic strain. So we implemented this one into the machine, but the machine data, real-time experimental data, includes more specific manufacturing environment. So we need to do some fine-tuning, transfer learning like this way, so that this one is FEM model. We did some fine-tuning with some experimental data, so we finally get this model. And then but during the manufacturing, the machines will make some different tolerance and shifting of the fencing, so then we need to continuously doing some reinforcement learning, so that we need to do that. And then finally we can make this model, so that our model can make some very fast 5 millisecond. Within 5 milliseconds it can make the decisions to how to make some control of the machine based on real-time data. Okay, so I'm gonna show you some this video to show you our system. This one is the control panel and feeding module and horizontal servo motor here, and then vertical servo motor here, and then this one is sensor module. We made a digital twin here, so if you look at here, this sensing data is a real-time sensing data. This is the real-time visualization in our digital twin. And also in this video I'm going to show you, we tried to make some flattening of 4 different coils with different curvature, and specimen 1 and 2, 3, 4, they have different thickness, different width, different material properties. Okay, we tried with 4 different specimens. The first specimen is here. So this one measure material property and dimensions, and you can see these rollers are moving. So, this is not clear, so if you look at this upside here, so you can see the digital twin will show you real-time movement of the roller. The first specimen is here, then we insert the second specimen here, different material dimensions, and then you can see here is moving, measuring the dimension and property. It is moving like this way, so that the second specimen, and we insert the third one like this way, and then you can see measure again, moving again. See that finally we did 4 specimens. You can see here even different dimensions, properties, curvature. We finally we got very the flat wires like here. Okay, so that we applied our technology into the wire straightening process. Then after that we are applying this technology into the bending, and also we are doing all the manufacturing process of the motor. Thank you for listening my presentation. Thank you.